Right, good morning, and I hope you had a nice half term. Here we are at the start of the last half term of summer, and it's still sunny. And look at that rose. That's Dave the Rose's older brother, Dave Senior. And here we are today looking at compound measures. They're called compound measures because they're a combination of two measures. So first compound measure is looking at speed, which is a combination of distance divided by time. Now, firstly, real life graphs. And on real life graphs, they'll be looking at time always goes along the bottom, okay? Time always along the bottom. Then up the side you could have distance or speed. Later on, by year 10, you'll be looking at displacement and velocity as well. So here we are, we've got distance up the side and we've got time along the bottom. This is a journey, I don't know, it's a journey of something going somewhere. Okay, so we know what I've done is I've labelled them A, B and C, and that's pretty good practice in an exam because then you can refer to them and the examiner can see what you're doing. So what we're going to do is we're going to look at each section. So section A, we took 10 seconds and we travelled 50 metres. Now, what that shows as a straight line is the rate at which we're travelling is constant. So if you imagine taking like a little section here and then mapping it across, or a little section here and mapping it across, you would see the same distance. So you're travelling at steady speed, okay, or constant speed. Steadily travelling along for 10 seconds and you achieve 50 metres. Okay, part B, time is ticking along, but your distance isn't changing, so you're not moving. So part B is constant speed. So part A is, that's part B. And part A is constant speed. Part B, you're just not moving. Time's going and you're not going anywhere. And C, again, is constant speed because you're covering distance at the same rate. Okay. Now, we'll look at the gradients and stuff of that in a second, but those are your main interpretations. Still and constant speed. So here, this is distance from. Here, this is distance. You have to be really careful in the exam, because if it was just distance, you couldn't go down. The graph couldn't go down. How can you travel negative distance? You can't. You know, the leather on your shoes is still being worn, even if you're walking backwards. But if it says distance from, then it can go back. So here we spend 20 seconds at constant speed, going 50 metres away from where we started. We stop, we have a little rest and a little look around for 30 seconds because it goes from 20 to 50, and then we go back. And because that's distance from, we can go down. It wouldn't be able to happen on the top one, okay? Right, and here we've got speed. Now this is different because obviously before we're looking at distance changing between over time, now we're looking at speed. Right, so this is constant, right, our speed is increasing. So this was constant speed, but because this is speed time, now this is constant acceleration. Okay, so we're getting faster and faster but at the same rate. When you get to H, time is ticking along. Your speed of 10 meters per second isn't changing. So you're not stopped, you're travelling at steady speed, the same speed, and then here you accelerate more. Okay, so in this graph you're going to be accelerating, going from 0 to 10 meters per second, then you're going to be travelling at 10 meters per second, then you're going from 10 meters per second to 15 meters per second. Okay, now speed can go down because you can slow down, otherwise that would be a bit weird, you just keep going faster and faster. So we spent 1 second and we ended up at 5 meters per second. Then by 3 seconds, from 1 to 3, we stayed at 5 meters per second. Then we slowed back down to 0 meters per second. So you've got to just, as soon as you get these types of graphs, lock into your mind, right, is it distance? Is it distance from? Is it speed? And then just have that in your mind and interpret what's happening over time. So like take little sections of it. You know, here I'll take a little section here, travelling at 5, little section here, oh, I'm still travelling at 5. That must be steady speed. Yeah, little section here, I'm travelling at 4, little section here, I'm travelling at 1. I must be slowing down. Okay? So how do we calculate stuff? Well, what we do is we use our speed, distance, time triangle. Speed is distance divided by time. Okay, now you can use this because you know distance is then speed times time, and time is distance divided by speed. So it's a very handy triangle. So if we look back at this one here for A, if we want to calculate the speed, we travelled 50 metres in 10 seconds. 50 divided by 10 is 5 metres per second. Part B, we travelled no metres in 20 seconds, so 0 divided by 20 is 0. And part C, we travelled 30 metres in 10 seconds, so 30 metres divided by 10 is 3 metres per second. So part C was slower than part A, and if you look at the graph, it's got a shallower gradient than part A, so that's why. Okay, so it's shallower. You know, here I'm going really fast and slower and slower and slower, and now I'm not moving at all. Okay, oh, excuse me. So we're looking at the gradient. So linking back to our straight line graphs, the gradient of a line is change in y over change in x, which is distance over time. Okay, change in y is distance, change in x is time. That's why the gradient on a distance time graph gives us speed. Okay, F, done this section here. So our distance is minus 50 divided by 30, because we're going back. Well, no, I'm thinking velocity, not speed. Ignore what I just said. Our distance is 50 because we're still travelling that 50 divided by 30, which is 1 2/3, or 1.6 reoccurring. Right, now the gradient of a distance time graph is speed. The gradient of a speed time graph is acceleration, because acceleration is the rate of change of speed. So it's your speed divided by time. That's why you have, so it's speed divided by time, so you've got time divided by time again, which is why you have meters per second and then a little -2. Okay, so for speed you can have, where is it? You can have, I'm trying to write on a sidewards here, meters per second -1. Okay, meters per second or meters per second -1, because it's meters divided by seconds. With acceleration, it's meters divided by seconds per second. Okay, because it's the rate of change of speed. So you just get, again, speed time graph, work out your gradient. 10 divided by 5 would be 2. There you go. So acceleration in that first part was 2 meters per second, excuse me, per second. So every second your speed is increasing by 2 meters per second. Similarly for H, acceleration is the gradient, and there's no acceleration because you're going at steady speed. And L, you're actually decelerating. So what's happening here is your speed is going from 5 to 0 in that 2 seconds. So your acceleration is changing by 5 divided by 2, which gives you -2.5 meters per second, or deceleration. Okay, that was quite long. On to the second compound measure. Now we have briefly covered this in the last video. This is density. So speed is distance divided by time, little triangle. Density is mass divided by volume, another little triangle. So examples, the units are firstly grams per centimetre cubed, or if you want bigger, heavier things, you use kilograms per metre cubed. So if I had a block of iron, now iron actually has a density of 8 grams per centimetre cubed. So a little tiny centimetre cubed of iron. Okay, if you think about centimetre as your thumbnail. So a thumbnail is about a centimetre across and centimetre there. So if you imagine it going back as well. So a block like the top of your thumb chopped off is about a centimetre cubed. Okay, so each one of those weighs 8 grams. So what we do with this block of iron is we firstly work out its volume. So we calculate the cross-sectional area, 10 times 3, times it by 2, so we get 60. So volume is 60 centimetres cubed. The mass is density times volume, so we use our little triangle. Where is it? Where's the triangle? There you go. We want to calculate the mass, so it's density times volume. And so all we do is density of 8 times volume of 60, and we get 480 grams. So that block, if it was made of iron and that size, would weigh 480 grams. Okay, block of cardboard, 70 kilograms per metre cubed. Now we're using, earlier I said for heavier things, actually you'd use kilograms metre cubed for lighter things, because it wouldn't make sense, it would be so tiny to use for something light. You know, one centimetre cubed of cardboard would weigh hardly anything. So let's have a look. So we've got density here, and if mass is this, what would the volume be? So now we know density and we know mass, so we look at our triangle, we know density and mass, we want to calculate volume, so volume is mass divided by density, which is going to be 350 divided by 70, which is 5 metres cubed. So that block of cardboard would have a volume of 5 metres cubed. Nice. Okay, an extension, changing units. This is only for the brave. Now if we had a speed of 70 kilometres per hour, you want to change it into metres per second. Firstly, calculate 70 kilometres, change it to metres. So that's 70,000 metres per hour. And change the hour into seconds. An hour is 60 minutes and each minute is 60 seconds. So that's 60 60s. That's how you do it. Okay. So all we did was we changed our kilometres into metres and our hours into seconds. Speed, 2 metres per second into kilometres per hour. So we change our metres into kilometres by dividing by 1,000, and our seconds into hours by multiplying by 60 and 60. So all we did to get, what's that, 7.2? So all we did was here, multiplied by 1,000 divided by 60 times 60. Here going backwards, we divided by 1,000 and then multiplied by 60 by 60. So just do it one unit at a time. Okay, density. If we want to calculate this into grams per centimetre cubed, well, 20 kilograms is 20,000 grams, because there are 1,000 grams in a kilogram. Now, how are we going to calculate metres cubed into centimetres cubed? We need to know how many centimetre cubes there are in a metre cubed. Well, if you imagine a cube, 1 metre cubed, and each side is a metre, each side is also 100 centimetres. So 100 centimetres in a metre. So 1 metre cubed is 1 times 1 times 1, 1. And 100 times 100 times 100 is 100, what? Is a million, actually, isn't it? 6 zeros. Okay, so 1 metre cubed holds 1,000,000 little cubic centimetres. So here, to convert metres cubed into cubic centimetres, we know it's 1,000,000. So you've just got 1,000,000 on the bottom. Okay, so it's 20,000 grams, kilograms to grams, 1 metre cubed converts to 1,000,000 centimetres cubed. So that's 0.02 grams per centimetre cubed. Right, well, anyway, that's it for today and this week, and I hope this all made sense. Bye.